like restaurants, yeah.
So you were talking about a perfect data set there, Stephen. Is that is that to do with your mineral stuff or something?
Yes. Yes.
Okay, and you have like loads of data, don't you? In like what do you call them? Like what program do you use to put all that in? It's this is it SAS or is it called Jump or something?
Are you talking about the images I produce?
Well, yeah, I'm interested in that as well. Like, what program do you use to organize all the data and then visualize it?
Okay.
And did you write those programs, or are you kind of using other?
No, I don't write programs. I've done some program writing through time, but sporadically, and very little have I done that supports my own work. It was mostly just to learn programming languages. But I use something called Golden Software Surfer for Windows, which is very expensive but very good.
Right.
And I have the latest edition of that on my computer, and they've just had a seminar that I attended as a video, where they're showing all kinds of new things about how to visualize geometrically well log data and so forth.
Right.
But I'm not into that kind of geology. I do my own thing.
Yeah.
And,
how would you describe how would you describe that? Is there a term for what you do?
Yeah, I don't know if Rajan knows anything at all about my work.
I don't know if he does.
I don't know much about that. Actually, I like to know, you said that, I think Christopher told me briefly about you, but I like to know more about what you do, what is your area of expertise or area of specialization, things like that.
I'm thinking it might be good for me to do some screen sharing.
Oh, yeah, absolutely.
Okay.
So I think we have to make you a host as well to do that.
That would help. Okay, here's a paper that'll help me talk.
Great.
Okay. So, where to begin? Refractivity has to do with refractive index.
Mm-hmm.
Okay.
Yeah.
You know, refractive index has to do with the speed of light through materials.
Right.
The speed is less than the light in a vacuum.
Okay.
And so if you take one away from refractive index, you get refractivity.
Okay.
In other words, let me see if I can.
It's almost like light bending, right? When you do
it has to do with light bending. Okay. So for instance, this says 720, yeah?
Yeah.
Uh-huh.
Okay, so that's a refractive index of 1.72.
Oh, I see. Okay.
Okay. So that's how refractivity relates to this.
Oh, okay, okay.
The reason I have these from refractive index of 1.39 to 1.87 is that's where I took my data.
Yeah.
Oh, I see. Okay.
And I took it, most work previously has been done at the average of these two Fraunhofer D lines. Here they are. And so the average is where most people in refractive index work have been reporting their results through time. Okay. So I concentrated a lot of data along there, but actually this is the D1 line. The upper one is D1 at 589.6 and D2 is at 589.0. So the average or the median of those is 589.3, which lies between.
Color, what? Excuse me. Color, what range it will be?
I don't understand you.
The color, what color range is that?
That would be sodium yellow.
Sodium yellow. Okay.
Yellow, or orange yellow. Okay.
Okay.
And in fact, this is a picture of the solar spectrum. These are Fraunhofer lines. And these are the actual Fraunhofer lines of a sodium spectrum that I grabbed off the internet.
Okay. Actually, Stephen, I'll just stop you there for a second. There's some weird interference on, is it on your line, or it might not be something that we can fix, but
I don't know what you're hearing.
It's just like kind of glitchy. Can you hear that, Rajan? Sort of glitchy, compressed voices or something. Rajan, would you be able to mute one of your microphones just for a second? Or I know you have, or switch your mute. It's probably not you. But just to check, and then we can just move on one or another.
Hold on. Let me, see, I have another line I put, but I switched off the.
Yeah, it's not a feedback issue, I don't think, but okay, shoot.
So we together again?
That's better.
Okay, so here we have wavelength.
Okay.
So this is the sodium wavelength of 589.3 in the middle of those two.
Okay.
I'm getting a lot of noise from what you're doing there, Rajan.
Yeah, I think that's okay now. But okay now? Yeah, there was just a bit of interference. It's still there, but we'll push on. So let's go.
Okay.
It sounds as though Rajan is playing with physical things.
I think it's just his phone. So Rajan, you can switch that back on if you want, because I was just testing to see if there was interference from that. Thanks.
Okay, so this is the line of most interest right here.
Gotcha.
And in my 1972 dissertation work, I worked on, I think, 6 different mineral species, families, and 7 different rock specimens from Hawaii. And I did all of the work with a sodium vapor lamp. But since then, I've worked on this specimen. I started work on this specimen on the 23rd of October, 1977. I finished gathering data on several systems in 2 different geographical locations, Hawaii and Arizona. I finished on the 10th of, I think it was November, could have been December of 1993. Okay.
Wow.
These dots represent what I call observation stations. Yeah. In other words, I went to this refractive index and to that light wavelength to gather 1, 2, 3, 4, etc. Points. And I went all told to 698 different places with 31 or 32, depending on how I count them, replicate locations. Okay.
Yeah.
So if you count the dots you see, a lot of them are so close together that they look like one thing. So you don't count 698 of them, okay?
Right, yeah.
But by the time I finished counting however many fragments I counted, comparing their refractive indices to the refractive index of liquids which had been previously calibrated for color and temperature, however many I counted was a statistical weighting factor, okay? And I counted, for instance, the least I counted, I think, was 31 fragments, and the most was somewhere above 200 fragments at that location. By the time I was finished, I had counted 76,798 fragment comparisons.
Wow.
Yeah.
Okay? So that's a pretty good data set.
Yeah, so this is what you mean about a perfect data set?
Yes, that's where I began.
Right.
But the data set was well constructed in terms of its design for how to collect the data, okay?
Yeah.
Because I read a book very closely before I began, and I learned to control for both catastrophic problems, like for instance, the microscope slide that I was working on broke, and it had a thermistor which had previously been calibrated for temperature in the center of it. And this happened more than once. And I had to recalibrate those every time it happened. Oh, I'm gonna lose unless I pay. This is crazy.
So, you also have similar problems there?
Yes, so anyway, we may have to begin this session again or whatever.
We have to restart. Yeah, we may go off and then we'll restart if necessary.
Let me see what I can do about something here. Minerals with these kinds of refractive indices down here,
yeah,
are well defined here, and there's a certain angle to things here that I've discovered.
right.
And it's kind of seen in these connection lines, which are from some previous statistical work done in Golden software,
Right.
which has kind of stuck around, and only much later did I see that those are angles I can use for my thinking. But that's one of the reasons this is kind of at an angle too.
Right.
Anyway, so these are the feldspars in here. These are olivines, it turns out. I worked really hard on this. It's forsterite olivine data. In here is the augitic clinopyroxenes, and here we pick up some more olivine. Okay, so these are extremely magnetic signals here.
Right.
Okay, so
am I right in thinking, Stephen, that each dot is a different mineral sample or multiple?
No.
Like,
no.
you know, if you just zoom in, I know, but like if you got...
Excuse me, wait.
Yeah.
You asked a question I can answer now.
Okay.
I'm working on one rock sample only.
Oh, okay, yes. Yeah.
Okay, this is one rock sample from Ukumehami Valley or Gulch on the island of Maui, Hawaii, where I collected a rock sample I could show you right now.
And so it is a volcanic, obviously, rock sample.
It's basaltic composition, but it's called gabbro because it's coarsely crystalline, because it solidified under the ground.
And so why did you choose that?
Because it's a fundamental specimen.
So
very fundamental.
It's like just been kind of forged in the earth and spat out, and it's like pristine.
It never got spat out. It got stuck in. That's why it has coarse crystals.
Okay.
It got contaminated the least by previous rock.
Okay. And so, yeah.
Weathered the least of all of 67 samples that I collected during my collection period.
Okay. So this is all of these, like, conceivably you could put a dot on every point on this screen if you had the
That's
time.
correct.
Right.
And the reason I didn't do that is because I was only interested in stuff here and in stuff here. And I'm trying to get stuff down in here and here that ties in with stuff up here, so that I can say whether it makes sense to collect data away from the place where everybody reports it.
Gotcha. Yeah.
Okay. So that I can produce a picture of the total rock surface, of the total refractive index for the total visible spectrum.
Right.
Okay. That's
okay. So some of this, the reason why they're collecting data in that band is because that's the visible spectrum. And then is this all the visible spectrum?
This is my visible spectrum. I was able to get dichroic filters cheaply at each of 7 of these Fraunhofer lines, or close to them.
Oh, I see.
And I was also able to purchase for more than $1,000 a variable monochromator toward the end of my work, with which I could go anywhere on the visible spectrum to 0.1 nanometer precision of repeatability.
Right. So essentially, you are trying to find out how the light behaves in this one, how the light is.
We're trying to define what the refractive index profile is,
so that you know how like in glass versus thing, how the light is bending, so that
chemistry goes with refractive index.
Yes.
Okay.
Okay.
So like photonic properties, are you trying to find some protonic properties also? I mean,
or you're saying that it's, oh yes,
things like permittivity and permeability are part of the study, but only recently have I been at all concerned with them. Most people doing optical mineralogy don't even know what that is.
Oh, okay.
Okay.
Okay. So let me back to the fundamental start of my work. In 1961, I was in a geology course. The professor said, geologists are ignoring refractive index to their own disadvantage. He also said in almost the same breath, more than once, some subjects have been removed from the literature.
Okay. Interesting.
Think about that.
Yeah.
That has to do with military secrecy.
Okay.
Okay.
Yeah.
So that's one reason I've had trouble publishing, I believe.
Hey, Stephen, you see this line that goes from the, you know, the line that everyone's working on? And then there's this dot way at the end. Yeah, near your mouse there. And then there's this line that comes out and goes to the far. Yeah, that one.
It's saying the best I can do to connect this to something is something up in here or something down in here.
Right. So you have this, this very jagged or like dotted line all the way down to the number 450 in the wavelength. It's kind of cutting across. Do you see that? And, oh no, not the Fraunhofer line. The statistical broken black line that leads up back up to where you had your first. 450? Oh, 450 on the wavelength.
Okay, 450.
And then there's like a diagonal line that runs back up to that yellow dot. Well, they're all yellow.
This
sorry.
One?
No, up to the one where the visible, where they're all taking their measurements from, on the far right of the screen.
Far right.
Yeah. Up to the yellow Fraunhofer line, the yellow one. Yes, and then over to the right. That point there is a black broken line connecting that down to like, well, it's not 450, but it's around there. It's like 432 maybe. No, definitely 440.
I don't know what you're talking about. I'm here, okay?
Yeah, if you go, you see that statistical black line that you have in there?
This thing?
Like, no, not the Fraunhofer line.
The broken one.
Yeah, yes.
The broken line that goes all the way down.
Yes.
Is that the one you're talking about?
Yeah, it goes through there.
Yeah, that one, right?
That's interesting. I haven't thought about it.
Oh, okay. We've got less than a minute, Stephen. Do you want to switch over to the other thing before? Because if you start a new subject, we're going to be out of time, I think.
You want me to try to get back to you guys by inviting you?
That would be great.
Okay, bye.
Thank you.
Okay, thank you.
See you soon.
Figure out how to get out of here. Stop share. Get out of here. Bye, guys. See you soon.
Yeah. Okay, perfect.
I don't know how much of my papers you've looked at, Chris.
I looked at all of the ones on this Canadian Journal of Applied Sciences.
Yeah, I don't know. I can't have too many things going and be able to work on this too. So let me see what's happening here.
Sure.
So one of the things that I have is this, and what happens if So here we have the refractive index -1 times 1,000, which is still refractivity. There's your definition of refractivity times 1,000. Okay.
Yeah.
So this is still a 1.570 refractive index. And these are the plagioclase feldspars.
Yeah.
And so we see that my concentration of interest is for what the minerals are that are really in the sample. And these are the forsterite olivine that I mentioned. And here are the augite group. And here is the pigeonite, which is strongly magnetic.
Great.
Here are some more olivines. And also I've discovered lately, these are probably olivines too.
Cool.
Okay, and these are most of the minerals that were mentioned by my advisor, Gordon A. MacDonald, chairman of the dissertation committee, in a sample that he described, which I discovered he described way later in my work.
Oh, something dropped off.
I'm sorry?
Oh, no.
Yeah, it's okay. It's okay now.
Okay, keep going. Yeah. What was this?
It's all right.
Anyway, these are the minerals that I'm really looking for in here.
Okay.
But tritomite is way down here and not part of, if you'll notice, not part of the data taken, where I took some things down in here. I was not taking things below here at the profile where I'm drawing, okay?
Yeah.
So the profile I'm drawing is really starting in here, and tritomite's down in here. So tritomite doesn't get covered. So because, in fact, I looked ahead and didn't want to be talking about tritomite when I was trying to talk about these things. So I didn't collect data on those lines, okay?
Sure.
And the reason this is not talked about is because I put it way out here for purposes of playing with statistics. Yeah. I wondered if I could stretch statistics if necessary to a kind of a phony point that I could hardly work at anyway. Yeah. And I wanted it to be really low. And I made it low. And it's a phony point. And that and one other point have been extracted, taken out of my data set, okay? Because for two places I wanted to be a phony, okay? So that's why you don't get stuff up around 187 here, okay? You don't get 187. I stopped, and more recently I'm stopping about around 170, and I'm not starting till something like 1490 or whatever, okay? So these are good data. And I've been able to identify what the names of these peaks are.
Okay, yeah, I see that. And they're the different feldspars.
Right, and these are all projected onto the 589.3 wavelength, okay? And this is a, you know, when I did this, I was saying, what are these? By the time I did this, which is a much more complicated model, as said here, yeah, I was by then saying, okay, these have to be volcanic glasses, okay? And these are percent equal. Well, what in the world do I mean by percent equal, okay? I count so many fragments. Let's say I count 100 fragments just for ease of thinking, okay? And let's say 10 of those, I say the refractive index is less than the refractive index of the liquid. Well, take my word for it. You have a halo that goes around, you know, it can be whatever shape, but if it's a circle, the fragment is, if it's a circle, it'll have a circular halo around it and in focus on the edge of the fragment. And if the microscope is pulled away from the sample, the objective lens is raised, then the halo goes either into the sample or into the liquid.
Okay.
It goes into whichever has the higher refractive index.
Okay, all right.
Okay, so I'm able to say this fragment has a lesser, equal, or greater refractive index than the liquid when I do that. Yeah. Okay, so therefore I can say, okay, if it was 10 less out of 100, then that percent is 10%.
Okay.
Okay. And if it was not a count of exactly 100, I have a statistical weighting factor because I kept track of how many fragments I counted at each of those yellow dots. And therefore I can say L over T. Okay.
Yeah, yeah.
And I can get a percentage anyway, okay?
Okay.
So these are percentages, and I can plot both equal, in both cases, this is equal, and this tells me I was at 589.3.
Yeah.
Okay. And these are like what percentage of equal I got at these refractive index locations.
Okay, so it's like a statistical average of all the, so you have to do the test over and over and over again, and then you get a weighted average or something?
Well, I got that number weighted. I got the model, and then I did a profile and got this picture.
Sure. Okay.
Let's just.
Okay. Yeah.
This, I was just showing you this.
Okay. Yeah.
This is a profile there.
Okay.
Okay. The pigeonite of great magnetic interest is located somewhere in here. It turns out to be right in here, and we're back into olivines here.
Right.
I've discovered lately. Okay, I'm not going to show you my most recent work because it's not published and I don't want to step on my own toes.
It's fair enough.
Okay.
Yeah.
So,
even so this is like a spectroscopic detection.
it is.
Method.
Okay.
Because I'm working at different wavelengths and I'm getting different elevations at different, for different models. Okay, let me show you. It's hard to know what to do next. Let me see if I can. Okay, here are, I'm going to show you golden software.
Great. Could
Here we
be.
go.
Ah, perfect.
All right. So this is a model of refractivity for space, shall I say.
Sure.
And this is the density that I got. Now, you see how peaked these things are? That's called mirromorphic.
Right.
Okay, you know about mirromorphic.
No, I have not heard of it. How do you spell that even?
M-E-R-O-M-O-R-P-H-I-C, mirromorphic.
Right.
So you can see here is the plagioclase feldspars.
Right.
You can see that things don't all line up on the 589.3 median of the sodium vapor line. It's a much more complicated surface than that, okay?
Yeah.
But here I have R, here I have D, and there's something called K sub P, which says if you take refractivity, that's refractive index -1, and you divide it by density, you get something called K sub P lately, but in the first place, it was called K. And that's what I've done here. I've divided this surface by this surface to get this surface.
Okay.
And this surface is again seen here. And I can grab this sucker. Whoops, I don't want all of that. I can grab this.
Right, so these are all different layers.
I'm going to grab this now, copy it, and I'm not going to mess with it anymore. I'm going to open a new. What happened?
I think you just want to click new.
I do. I want to open new plot document, and I want to paste in what I just got.
Perfect.
Right there you have.
I want to get rid of this.
Okay.
I want to get rid of all of this.
Yep.
And we're only interested in this stuff here.
Sure.
If I click on that and go to contents, I can see that I'm on the surface. That's all very good and well, but I want the map. And then I want to say, oh, let's do that.
Oh, cool.
Oh, these all you program these things?
No, this is the Golden Surfer software or software surfer.
Golden software surfer program.
Okay, it looks cool.
Okay,
it's like an imaging editor and statistical program all in one or something.
Yeah. Okay. So we got all this going, and this has to do with the one that we just came from. And what I can do is zoom in.
Yeah.
By just, unhappily, it doesn't go to exactly where I point.
Right.
Also unhappily, it pans, but it also rotates when it pans.
Okay. Well, it's not doing it at the moment. But that's interesting. So that is a 3D image. Wow.
So you can profile the geo surfaces like that?
I showed you a profile.
Okay.
That's what the profile was across. You can see where the data are.
You mean from 610 down to 560 would be the profile in the wavelength, or?
My profile was at 589.3.
Oh,
589.3 profile across here. You can see where the data, see where this line is? That's showing that there are a lot of data along that line.
Okay.
Okay.
Yeah. So is this all interpolated, or some of that will be interpolated, or?
This is a model of all that area.
Yeah.
After I divided one model by the other, remember?
Stephen, I have one question.
Yeah.
I have one question, Stephen.
Okay.
Will you be able to analyze like moon rock or Mars?
What about it?
Will you be able to analyze those with this one?
My whole purpose, remember I was told that geologists were ignoring refractive indices to their own disadvantage?
Yeah.
Okay. My question was, I said, sir, is it possible to get meaningful data without orienting any fragment to a known optical orientation before comparing its refractive index to that of the liquid? And the answer was, if you do statistics and probability, you might find something out.
Oh.
So my whole purpose of all my work has been to see how much could we tell about a rock sample or a mineral sample by doing statistically significant creation of statistically significant data sets. And this is the result of my work. The answer is yes, you can get statistically significant data sets to the point of being able to talk about refractive indices that way.
Yeah.
Instead of rounding after 3 decimal places or maybe 4. Most previous good work in refractive indices has been at the 0.0002 RI level.
Yeah. So you're going way further than that.
I'm going to machine level.
Great. And that's another thing about those data sets that you can run a lot of statistical stuff just straight off the bat with it. Like click a button and it will do like the average and give out lots of stuff like that. So this is the density or divided by D, was it?
This is K.
Right. So, okay.
This is going back here and looking at everything.
And so are we kind of filtering out using the background data to filter out something, or?
We've gone a long way from where I started talking. This is refractivity, and this is density, and this is divide this into that, and you get this.
Okay.
So these are refractive indices, but these are no longer probability levels. This is density estimations. And this is the K sub P. And if you'll allow me, I have this old book.
Yeah. Microscopic.
Okay.
Yeah. Microscopic determination of
or some technique.
Nanopack materials.
This is
microscope.
Very good.
Geological Survey bulletin number, which is online free.
Okay.
Oh, you use the data. Okay.
Okay.
Use their database.
Okay. I use their database, and I go to a chapter 3, which has been redacted from the most recent version of this book.
Right. Interesting. Okay, we can't really read that.
No, I'm sorry.
It's a bit blurry, but that's all right.
This is where K sub K, but not yet K sub P, is being defined in here.
Excellent.
Okay? And they did a 1986, I think it was, version, or 83 version of that, where they took that whole chapter out.
Oh.
My most recent paper has to do with K sub P.
And this is, it's not there in the literature anymore.
And well, the K sub P is there, but not in the literature that I go to.
Okay.
And for instance, somewhere here, I don't know if this is it. Oh, here's the guy who did the, he said, you take my K and you divide it by chemical data, and you come up with something called the Mandarino, what I call the Mandarino Compatibility Index. Okay, that's where my most recent work has gone. Okay, this is the copy of the work that I just showed you, which is in ArchiveX, or however you say that, RXIV.
Archive, I think.
Yeah, and my first version of this was submitted to the Canadian mineralogist, where Mandarino, wherever he went, did his work. Okay, he did most of his publishing in there. So this is essentially the paper that got rejected by them in the first place.
I remember,
because I didn't do any interpretation. I have flashed by you some interpretation today that I don't want to show you any more of.
That's fair enough.
Okay.
It's a very interesting research, and it's been great. That's great. You have unlimited minutes. We had that for the last Zoom session. We did like 30-minute presentations, and it worked fine. And I completely forgot about the time limit on this one.
Okay.
But it was really interesting research. I had a few questions about machine learning or the linear regression aspect with the the way you can use weighted values in linear regression.
Yes.
Is that something that you do? Is that what you're referring to when you talk about?
Absolutely.
Okay.
One of my papers touches on that. I forget which one it is at the moment.
Yeah, I think it might be on ResearchGate. I'm not sure though.
This isn't it.
Okay. Did you get something
Here
about?
we go.
Oh, cool.
All right. Now, for instance, let's see if I can make this so I can look at it. This is not the neatest one. No, here we go. Somewhere here. Is this it? Not yet. I'm sorry.
No problem.
Okay, so you're asking about weighting, and I was hoping to find, you see, this is JMP, okay?
Yeah.
JMP is part of SAS, okay?
Okay.
And this is how JMP does my, what is effectively general linear modeling. They don't call it that, but I had one of their experts before she retired help me get the same result from the way I use their program that general linear modeling gave me from Statistica for the same submitted data, okay? Yeah. And what happens is the lower these bars, the less impactful these inputs, these independent data, okay? And for instance, here we have squares and cubes of things like the particle temperature or the liquid refractive index temperature, or gravity times weight, mass, you should call it, times, I forget what that was, but this is essentially gravity.
Would that be seconds?
In gram?
Seconds?
Yeah, gravity.
Gram, meter, second?
Yes, yeah. That's it. Thank you. And so in the one I was looking for, there are 3 things at the bottom, and each of them has to do with statistical weighting. Okay, I told you that I take care of, there's how many fragments I counted at each station for each case. I counted so many fragments compared, okay? either 31 or 120 or whatever it was. That's a statistical case waiter. But there were two other things that I kept track of. One was, how many days into the experiment am I? Julian calendar referenced back to 0 through however many days. The other was, what is the ohms reading on my step decade resistor box that has to do with controlling the temperature? And that's different for each thermistor that got involved with the experiment. So that has to do with, what do they call it? I'm sorry. One has to do with drift of the instrument, and the other has catastrophic failure. If I broke the slide and I had to go with a new thermistor, then catastrophic failure is tracked by how many ohms I set to get a given temperature. So those three became valuable, but they are not like 0.0001 p-values. They got to be less than this each, but if you put them all together, they were important enough to keep around because I knew that they were important. Okay. Yeah. So it turns out that you see, you might guess by now that I know pretty well what the refractive index of the liquid was, and I know pretty well what the wavelength was. But what happens is I also know pretty well what the L% and what the E% were. In fact, I know those percentages almost as well as I know the values at which I set the system. And that's kind of rare. Right. And that's why I said I've got a perfect data set.
Yeah. Okay, so yeah, there was something I was going to ask. Remember you said you found this value, which was close to 19.5, and then you altered it to make it 19.47?
No, I didn't alter it.
Oh, sorry. I think you said that it would be better or something if it was 19.47. Well,
you see this angle here?
Yeah.
It's something like 13.5 degrees. I forget what it is by here, okay?
Okay.
But what happens is when I'm doing a statistical model in Golden software, I have, let's see if I can find this is the underside of one of the best models I ever did. And you can see that it's hanging together by just a little bit. Right. These are non-magnetics. These are magnetics.
Okay.
Permittivity, permeability. Save a little space by getting rid of this.
Do you, Stephen, forgive me for interrupting. Do you use fractal theory? Fractal dimensions?
No, I don't do that. But I have Mandelbrot's text within reach.
Okay.
If necessary.
Like Eisenhower dimension, things like that. Yeah.
What is it, Raja? Just
Eisenhower dimension, like 2 point, like you have snowflakes.
Oh yeah, yeah.
Just 2 point something, 2.3 something dimension. Yes.
Yeah, I like the idea of fractional dimensions.
And the postal line, you know, just 1 point something it will have. So
let me say briefly that I was studying a thin section before that book came out, and I was trying to figure out what the perimeter was on a fragment in the thin section of rock. And I decided that it would be a longer depending on how I measured it. And that's what got him into fractals. And I decided to.
So you know Mandelbrot then personally?
No.
Oh.
But before his book came out, I decided that I could not take on the study of what the perimeter value would be on on a fragment like that because it would grow depending on the size of a rod that I might use to measure it.
Oh,
and
yes.
that's exactly what started him off.
Okay, yes.
All right. Only he was working with coastlines.
Yes.
Well, I've worked for the Naval Oceanographic Office measuring the bottom of the ocean depth. And my master's thesis was on the Tuscaloosa Seamount, which is off of Oahu and thought to be either landslide or volcanic, or I think now both. And I've done quite a bit of work with geography and so forth. So I was able to relate to his thinking, but I couldn't tackle that job. So I'm not finding in this particular set of images what I was trying to think of to share with you.
Yeah, it was around the 19.5 issue. And I just thought that was interesting because you have this, yeah, check this out with the crop circle here. And then you have this, what do you call it? Like an octahedron or a star tetrahedron. And then if you were to superimpose that on the planet, and you can do it with Mars as well, the points can be lined up, or the latitudes of the star tetrahedron line up with, you know, it comes out at 19.47 degrees, and that lines up with, it can be lined up with the volcano at Hawaii, right? Which is where you got your rock sample. So I think that's an interesting coincidence. Is that important in your work, or is that just merely incidental?
You're talking about my friend Elvira.
Yes.
Diego in Argentina.
Okay.
Okay. She's the one who did all that, and I'm in touch with her, and I keep waiting for her to send me something in Spanish so I can translate it into English. So, you know, I can even show you somewhere here if I find it.
This is kind of sacred geometry almost.
Yes. And this is, I think, maybe it's not. Maybe
okay.
This is what I want.
And so can you describe her work for us, or even briefly? Or?
I'm not even going to try, but you can go here.
Very good.
You can go here, and your people can go here and find out all about her work because it's there.
Nice one. Will do.
Right?
Well, there was another guy called, no, his name escapes me now. I'll think of it later. But Richard C Hoagland, I think. He's like a researcher back in the 90s and early 2000s who did some sort of interesting work, but I don't know what he's doing at the moment. But he was big into this concept of like the 0.47 and this sacred geometry point. I don't know if it was his research or someone else's, and all about geometry. Yeah, I think it was his research, and all about like how important volcanoes would be located at these specific kind of tension points on the Earth.
Right.
I just think it's interesting that your rock is from that same location on the planet. But
well, she thinks it's interesting as well.
Yeah.
But I can't speak to that because it's beyond my knowledge base.
Okay, that's fair enough. So
I would like to have her continue her work with me, and maybe we can work together to bring those two together. She's quite excited by the fact that let's see, how can I know what I can do. Maybe
she can probably come into our Zoom session also, if it's possible.
You want to see about our friend if he's here? I'm going to stop sharing my screen.
Okay.
It gives me the ability to go down here and see where is this thing? There it is. I don't see any sign of him in participants, okay?
Yeah, that's fair enough.
Okay, so let me not do any more of that, please.
Yeah, I sent him, I didn't get any reply from him. See, one other thing, Steve, we are interested. I don't know how much, you have Hawaii connection?
Yes, I lived there for many years.
Okay. So one of the things we are interested in, you may be interested. We're going to start like a Hawaii conference, probably late 2022, 23. I was talking to somebody.
I'm sorry. Are you talking about R2D2?
No, we all get together there. You know.
I see.
Yeah.
I don't travel.
You don't travel anymore?
No, believe it or not, I'm 81 years old and nobody pays me for anything I do. And I don't have money.
Yeah, fair enough.
Actually, we plan to raise some money, but later on. That's another thing, 50%, but yeah.
That's interesting. I was talking to people actually who are from the States, I think, possibly Hawaii, and they were looking to fund some projects. You know, if someone had a good idea, they would look at it, and I think they're in the construction business out in Hawaii, so they might be interested in putting funds towards it. Rajan, I'll send you on their details.
Okay. There's a girl they can come on Zoom if you have connection. And we can discuss about that one time, you know, we can discuss about that.
Yes, I mean, sounds like a good idea. It's just an interesting coincidence.
Yes. Yeah, we are trying to find ways to. You know, I talked to some people here, but they are put away because their family had some COVID problem and things like that. But I don't know whether they'll come back. He had good connection, and he was telling he has, you know, exactly East-West Center. He said the University of Hawaii is the best place, and he can arrange those things. But I don't know whether he can come back now. But Christopher, your contact may be a good thing, and let's pursue with that. And they can come on Zoom one time. We can discuss about planning those things and then how to go about.
Yeah, I'll get onto them. Maybe I'll just email them. I mean, I don't know them. They were just reached out to me, so I've got to be a bit cautious. But you know, if we have an idea, and you know, if you want to throw something their way, maybe a couple of ideas.
Partly sponsor, and we can. That will be great. Yeah,
as long as they don't just like run off with their ideas.
Yeah, and also global warming. You know, that's one thing I am interested in.
I'm not at all interested. That. I'm sorry, I'm not at all interested in global warming.
No.
I'll run away from immediately.
That's fair enough. But it's a great resource for maybe funding or something. Yeah.
Not for me.
No, yeah. Actually, I've never.
You don't believe in that.
Either, but...
No, I don't.
Okay, so there's a couple of other things. I'm just interested. So why this rock though, Stephen? Like, what is the significance of it?
It's the freshest sample I could find of a Hawaiian basalt.
Right. So
that's
it's kind
gabbro.
of. Is it like?
I went to Maui because Maui is dissected enough to cut down into the plumbing of the volcano.
Great.
And
what's your opinion of the La Palma volcano going off at the moment? Are you tracking that, or are you?
I've seen it.
Yeah.
I was warned that it could wipe us out, and maybe I should take the family and flee west and to higher ground if it sent a tsunami in this direction. And I've been in Arizona where everybody who thinks about it gets worried about Yellowstone going off and flooding the place with hundreds of feet of volcanic ash. And God will take me when he takes me, and I'm not going to worry about it.
Yeah, exactly.
Yeah, I went to that Old Faithful one time.
Did you?
That was long ago in Yellowstone.
I've been. We drove around Yellowstone when I was 12 years old, but I've never done that.
Also, it was fantastic. The Old Faithful every half an hour comes up.
Wow, it's very strange. Yeah, I've heard about it. It's filling up with water, and then it's like you can set your watch to it or something.
Yeah, it's just fresh water, just spring. This thing, spring.
Yeah, it sounds like an amazing place. I've never been, but I've seen plenty of shows about it.
Yeah.
So this rock is in a way like is it like a perfect specimen or a reference specimen or something?
It could be.
Okay.
It's probably uncorrupted, very native, very original. This thing, right? Uncorrupted by the environment.
It's the least weathered sample I could find.
Okay.
So
it's very original, or raw material.
As fundamental a stone as I could pick up.
And so is it this kind of like does this lead into chemistry and?
Oh yes, but
and
not by me.
Right, and this is other research that other people have done, possibly off the books.
Mandarino.
Yeah.
Mandarino. Excuse me. Mandarino divides my Kp by his Kc for chemistry, and gets a compatibility index. And in the process, all through the literature, people are faulting my K because optical mineralogists never created statistically significant data. Okay.
Yeah. Why not?
So why not?
Yeah.
Because let me see where I am here.
Yeah, we were talking about the chemical thing, and then I was saying, why didn't they have a statistical, why don't the geologists have a statistical significant?
All right. So you see the plagioclase feldspars?
Yeah.
These are all in the one specimen of rock I've studied so well.
Okay.
All MacDonald could say was that there was plagioclase, and I think he called it labradorite.
Okay.
But labradorite, he may have said bitonite as well, but he only saw this. When you look in a thin section, let me just kind of draw a fragment here. You see zoning chemically. And if you break that grain up and powder it, you could get any single fragment from anywhere in here. And when students are given the job of discovering what kind of plagioclase feldspar they have, they're given something like this ground up, and they don't know what they're doing.
Okay.
They grab a fragment and they bring it to a known orientation, and they finally get it to match a liquid. So they say, oh, it's a whatever they say. But they don't know which of these compositions they picked up in one fragment. You see what I'm saying? They certainly don't want to do it 8 times minimum in order to give it an average. It was hard enough to do it once.
Yes.
Okay.
So that's the statistics. They're not adding in the statistics.
There are no statistics involved in optical mineralogy.
Yeah. So they're just taking what, and that, so their answer could be wrong, could it? Because it could be all.
It's right. It's right for the one fragment they get. But even in 0.038 millimeter size screen that I used to pass my entire sample through, including all the opaques that were very hard to break up and get through the screen.
Yeah.
Even in a teensy fragment, you can see optical changes. You can see that, oh, this part of the fragment is lesser. This part is equal. This part is greater.
Right.
In one fragment.
Yes.
Reproducibility, right?
Reproducibility.
Okay.
Most optical mineralogists never get to statistics.
Okay, so you're
in fact, most geologists run like hell away from the subject of optical mineralogy. Because I was taught in 1961 that optical mineralogy was being ignored by geochemists because they didn't trust the data. And I believe that's still to be the case, which is why optical mineralogy has dropped out of college and university curriculums.
Okay.
Unless you want to say curricula.
Okay, yeah. Fair enough. So that's interesting. So, I mean, to just go on a completely different topic here, Stephen, that's kind of tangentially related to your work, the crop circles. Like, you know, what is your opinion on that as a phenomenon? And
yeah, I do not believe that man makes those.
Cool, right? So you believe in the alien theory, or like?
I'm not afraid of thinking about aliens.
Yeah.
And have you followed the work of Stephen Greer?
I do know Stephen Greer. I know he's done some stuff on giants. But I wouldn't be like hugely familiar with his work. Actually, no, I do. I'm thinking, and then I'm mixing up with Bob Lazar, but definitely Stephen Greer I've heard of.
Do you believe in aliens or no?
Who, me?
Yeah.
I'm not afraid to say that it's possible. And because I don't think humans make crop circles, icicles or popsicles.
Yeah.
But anyway.
Like a sickle.
Yeah, I guess I believe in aliens by now.
Fair enough. I mean, there was a lot of stuff about aliens from the government this year, wasn't there? With the
UFO sightings.
That's right.
Yeah. I mean, because the Navy, they were measuring some things. They said there's no way these kinds of dirigibles could be attributed to any non-earthly flying objects,
Right, it was so the USS
Nimitz
or something, and you had these radar signals of these triangular craft.
Very fast. It's much faster than anything that on Earth can do, any flying objects can do. And it suddenly changes direction and all those things,
This is the famous Tic Tac. Is it, Rajan, that you're referring to?
Yeah, the recent one, they were actually to a Congress. They are reporting to a Congress. They are presenting because Congress has called them, and I think the president also has some special commission on this now. If I am not, the previous president Trump also had some people presented. So they are considering from Pentagon. They are now considering seriously, but they don't have any reasonable conclusion. They have not reached any viable thing, like the global warming. They are still at odds, The people who want to believe in aliens believe in them, and they don't want to believe in them. So they skew their data accordingly, Everybody skews their data. That's the problem.
I'm not worried about it.
There was a movie with Charlie Sheen in it called The Arrivals, I think it was.
I haven't seen it.
You haven't.
First Contact, E.T., First Contact, they were the famous ones, but.
Yeah, exactly. Like he's like kind of with the Arecibo project or something. They're listening for aliens communicating with the planet, and the whole point of it is that it ties in with this global warming thing you're talking about, where the aliens are like heating the planet up so that it's more amenable to, because their planet is warmer. So they just decide,
there was a brief period of time when I thought I had contact. Very brief.
Yeah. And was this in the States, Rajan, or was this in?
Yes. When I was in India once, but in States also, about 10, 20 years ago, I had, occasionally I have some kind of transmission I get, and it cannot be earthly beings. That intelligence is much beyond our human capabilities.
And was it a telepathic thing, or?
Yeah, telepathic. And you have to reach. There's if you go to the neurology, our brain, on our brain, there's a Hawaiian sutures on top, right?
Yeah, yeah.
What happens that told me, I was looking at, I can reach that through meditation, things like that. And one of the things that the theory showed me that, the crystal skulls versus our skull is like kaleidoscopic skulls, which means that it's possible. It's just a theory now. I mean, it's just a hypothesis
that we traveled from there. We had crystal skulls, but it broke up. It broke up and made into kaleidoscopic skull.
Okay.
That's what we are. That's why we have Howards and sutures.
You'll have to, I'm going to ask a few questions about that, Rajan, because I'm not sure I understand. So in my head, this is what I think you meant by that.
Yeah.
There was a crystal skull like on another planet, and it traveled here or another dimension. And then when it reached Earth, it split into like loads of different crystal skulls. And
no, the crystal broke. You know, if you have a crystal, it breaks. It forms kaleidoscope. It can form kaleidoscope.
I didn't know that, actually. That's news to me. Okay, so, because I've never heard of a broken crystal skull before.
Yeah, and that made sense to me. This is the transmission I got, you know, the wave transmission.
Okay.
So it broke, and then the nature was, you know, we evolved. We evolved into a next creature. That's why we have all these hands and features, but the aliens are different. They're not limited by, see, our hands and things are limited.
Yes.
You know, our hands and this has some limitation.
Yeah.
Well,
we're like mortal, aren't we?
It's as if we are disabled aliens. We are disabled aliens, you know.
Okay. So did the aliens build the crystal skulls?
No. I think it's formed out of nature. Formed out of nature.
Oh, really?
So that's
they're natural objects.
Yeah. So they're higher intelligence in the sense that we need a lot of different things to understand things, right? We have to write, we have to do video separately, right? They don't need to write. Everything is, the brain records everything automatically. And everything is there. All the forms are there, and they don't really need text. So that's why if you communicate by text, most likely they may not respond. We have to have
sorry, if these crystals, this crystal skull broke or whatever, and did it form more life on Earth then?
Yes.
Okay. So, but it was
most likely in the sea, under the sea, like Atlantis type of thing.
Yeah. And so are we kind of like, according to this transmission you got, we are like the, how would you say, the sort of broken children of this skull or something?
Degraded form of aliens.
It kind of reminds me of the Bible a bit, you know, the fallen people, you know. It's a similar kind of concept.
You know, we went through so much stress. I mean, we're evolution process. We have to learn a lot of things, whereas they don't have that problem. That learning is not necessary for them.
Wow. Right. So are they kind of all instinct then?
Yeah, it's automatic genetics type of thing. It's a genetic transfer. It's a direct transfer from brains to brain to brain transfer. Crystal skull to crystal skull transfer. Maybe it's spectroscopic or some kind of a wavelength. You know, we can only imagine certain wavelength tuning into certain wavelength, and the brain has a power to tune in. So if I tune into certain things, automatically that particular information is transferred. And the other way tuning, it will transmit the information. So you don't need all these different things. So what happens is the crystal broke. This may extrapolation broke, and then some of it went to our hands, some of our legs. So we have to use all of that. You know, it's not connect. Oh, Manuel is coming in. Okay.
Hey, Manuel.
Hi, Manuel. I don't know whether he can see us
or hear us.
Yeah, but the thing is that, so what happens if we need hands? We need a coordination. We have to learn a lot of things as we grow up. They don't have all these things. It's automatic for them. It's automatic. This is, so we are highly disabled. Our five senses.
Yeah.
You can just say we are highly disabled, and we are trying to habituate ourselves.
I think that's correct. That seems very, I like that interpretation of what's going on.
Oh, yeah.
So, Stephen, you're showing some interesting data here. What is this?
Okay. You answered my question before I asked it. My question was going to be, do you see? And you do.
Oh, telepathy. I've got it going on.
Telepathy.
Do you see that it changes? Have you seen that it's a movie?
Yes, I can see it moving. Yeah, it's very good.
Okay, so you see these lines here?
Yeah.
That rectilinear bunch of lines means there's really no data there.
Oh, okay.
Okay.
Right.
And where things are really well detailed, that's where the most data.
Oh, he's telling us. Oh, he's now communicating with us.
Cool. So you've got
Let
like
me chat with you.
It's a map, isn't it? It's a surface. It almost reminds me of some kind of icing
so he's
model.
saying hello to us here. You see that?
Oh, cool.
Okay. So I hope he can hear us. I can't.
Oh, he can't hear.
Okay. So hi. I can't slow down to talk to him in typing as I.
I'll say hello for you.
Maybe you can translate for him as we go here. But what we're seeing here is, I'm going to get out of here. I need the space. What we're seeing here is plagioclase feldspars, glasses, olivine, clinopyroxenes. Okay, we're looking down at one of the best models I have of E%. We're looking down at E% probability levels coming out of the page. Okay, we have refractive index along here, just like every time. We have wavelength here going from low to high. 589.3 is somewhere in the middle here. Okay, this is an interesting place where I really studied a lot just to find out what was happening, low levels of olivine. And what's happening as you see the tan come in, it smooths out what otherwise is low data. And what it's doing is it's correcting the base level of the model, and it's giving us finer detail. Something like the highest peak here was 27 or something, goes to 29, or maybe my numbers are a little bit off. But as this comes in, the model is corrected to give finer details in the probability levels.
Okay, what is the X and Y axis again?
This is refractive index. This is wavelength.
Okay. Oh yeah, of course. Sorry, I should have known that.
That's okay.
Okay. Just to make sure, yeah. Refractive and Y.
So you can see that it's really dangerous to take work done at some other wavelength and project it down to here and tell people that you've done something. What you've done is confuse the issue. You've confused. You cannot do that. People, I was told in 1961 or so, that people were taking work done at other wavelengths and projecting them back to 589.3.
Okay.
You better not do that, because you're just going to confuse everybody, including yourself.
Yeah, it sounds like a bad practice to have.
That's what this tells me.
All right. So, yeah, like if you could convert the wavelength down, like shift it down somehow, that could work maybe. Oh, and so is 589.3 or however you say it, here. Is that like a chosen, agreed upon wavelength?
Yes.
Right.
Yeah, that's the average of the sodium Fraunhofer lines.
Okay. And so why do they pick sodium?
Because it has the strongest, where are we here? I've gone away from this. It has the strongest Fraunhofer lines. It has what they call the doublet. There are others that also have doublets, but there are none so strong as sodium. And I think there's a reason for that. The sun yellow, you know, that's the color of the sun, is predominantly sodium color.
Golden, yeah, golden yellow, right?
Yeah.
When I was young, the sun was yellow, and then in about 2010, it changed to white. Has anybody noticed that?
Yeah. You know why?
Well, I've heard
geoengineering.
What?
Geoengineering.
Yes. Yeah, I heard that it was the opposite, though. That it was like they'd taken out a lot of pollution in the atmosphere, and the pollution used to make it yellow. That's what I was told. But go ahead. What's your theory? Do you have a?
Oh, he can see us. Okay.
Yeah. Cool.
No.
So what do you think, Stephen? Then do you think there's a different, like, so that they, like, what could remove? How could they be adding spectra to the sun with geoengineering?
They have put so much crap in the atmosphere that it gets between us and the sun.
Yeah, but wouldn't that be blocking? Wouldn't that block stuff? So how can you? Well, like if you go from yellow to white, that's adding wavelengths, isn't it?
Yeah, you're getting scatter, and the scatter ends up hiding what's really there. It's hiding the solar spectrum.
Well, that's plausible, I suppose. From like you have like scattering matrices up in the atmosphere. Like why the well, I think blue light scatters the most, doesn't it? So that is why the sky is blue.
Rayleigh scattering.
I mean,
they put all kinds of stuff up there, and it screws up the spectrum. One of my thoughts was to do microscopy using the sun directly. I have taken a diffraction grating, I have put it on a chair on a universal ball joint, and I have aimed the spectrum of the sun into the laboratory at my microscope sub-stage mirror, and I have cast that light onto the ceiling and not dared put my eye there, and put in place a cap from a medicine bottle, and blocked so that I dare look. And when I did look at a thin section lit by such sunlight at a chosen wavelength, I saw swirls of things happening.
Yeah.
As though I were looking at a cloud chamber.
Uh-huh.
I mean, you have gamma ray also, right? Gamma ray comes through.
And in fact, I did one experiment where I instead of taking data away, for instance, let's say nowadays I only look at data in here, in here, I can't get it to go straight, within some arbitrary, let's say like that is what I'm looking at.
Right.
Okay. Because edge effects from stuff down here where there are not enough data can screw up what's really happening. So I get within the data to look for things that matter around in here. Okay. So one of the things I did was instead of limiting from here to here, I said, okay, what if I go from, let's say, 0 refractive index to a very high value out here on the right? And what if instead of the visible spectrum, I allow from very low, I forget, to like 10,000 or whatever wavelength I put up there? And I did a model, and nothing plotted within my data set. And I found stuff that looked like maybe gamma rays. And in fact, somewhere here, I may have an image of something on that. I don't know.
Where would the gamma rays be coming from? Is that inside the material, or?
You get gamma rays coming from wherever.
Okay, like all from throughout the universe.
Yeah, and maybe even in my light source somehow. I'm no expert at gamma rays, but I'm sorry, I don't have that particular thing. I think I put something out on ResearchGate about that particular game I played.
Okay.
It blew me away.
You were also talking about, do you have any opinions on things like dark matter or, you know, that kind of thing? Yang-Mills, I think you also have a paper on.
I mentioned Yang-Mills, but I don't know enough about it to really know what I'm talking about.
Okay, that's fair enough. And the as for dark matter, do you have a strong opinion on that?
Let me see what I can do to help us talk about that right away. I don't know if I did this here. Shoot. This is not helpful. Do I have this?
That's P. Contreras. Yes, he also publishes on Canadian Journal.
No, he doesn't publish in Canadian Journal. You asked
okay.
about dark energy?
I'm thinking about someone else, sorry.
You asked, excuse me.
Do you believe in dark energy?
Would you please let me speak?
Go ahead there.
You asked about dark energy. Here is an email I wrote to Leo P. Contreras today.
Uh-huh.
Oh.
Big thing. Yeah, I've heard of this.
I came across this paper today. Yes, I'm interested in dark energy. Do I know anything about it? I know nothing. However, my second paper this year may be about this.
Okay.
Yeah, we are trying to get to that with our gauge theory, things like that. I think we will advance to that eventually.
Well,
we have a model, circuit
this
model.
Paper may interest you.
Sure.
You can share it with us, yeah.
So you would, but dark matter is a different thing, isn't it? Is dark energy is causing the expansion of the universe, supposedly, or it's definitely related to that.
There's so much I don't know that all I can do is share that.
Cool.
Okay.
No problem.
P. Contreras has told me not to talk quantum mechanics.
Okay.
It's outside my realm, and he will fight with me if I say quantum mechanics. On the other hand, I told him I had a meeting this evening with people interested in quantum mechanics, and he said, good, because he's arguing with me.
Nice one. Maybe we should get him on, and he can tell us more about the subject as well.
He has never come to any Zoom meeting aside from one-on-one that I have invited him to.
Fair enough.
He just doesn't.
Yes.
He speaks English, right?
He does. Yes.
Okay. So
you keep wondering about how I got involved with 19.47 degrees.
That's
and
right.
I never quite get to telling you how.
Yeah.
And instead of trying to show you how, I'll just plain talk. What happened is I saw that if I rotated the search engine in terms of modeling with Golden Software Surfer, I could stretch the model so it would look for narrow X and long Y and turn it. And I found that I found it by using JUMP and doing a hierarchical clustering analysis. And I saw that there was a 13.5 or so angle in there. And I tried that, and I got improved returns in the statistical report from the Golden Software modeling fit.
Yeah.
So I did that for the entire model. And then I discovered that the residuals were 0 except for the magnetic fraction. And I discovered through some chasing that if I did another 19 plus rotation for the magnetic section, that it got better too.
Right.
That's how I got to talking about 19 point whatever. And then I discovered this guy you're talking about, not my friend in Argentina, but this other guy. And I put it in my ResearchGate blurb, okay, about things like crop circles and sacred geometry and so forth. Are you familiar with Nassim Haramein? Yeah,
I've heard of his name. I know some of his research, not a whole lot.
Okay. You should chase him. You should. I support him.
Cool.
I can go to his monthly meetings and leave him questions that he mostly ignores, but people can ask him questions, and he does respond. And he has some very interesting work that he keeps promising in the next paper.
Yeah. So that's interesting. There's something about the angle 13.5. I think if you go 13.05 is the Weinberg angle, which is used for, do you know this term, Rajan, mixing in quantum physics, quantum particle physics, where you have like the up quark mass, and then it's basically like a probabilistic thing where the up quark can have the mass of an up quark and a down quark, let's say, superimposed. So it's both at the same time. And the way the two are related is by the angle.
Is it connected with the Higgs boson or anything?
It's more along the, like, it would also connect with neutrino oscillation, and the fact that like one neutrino can turn into another neutrino. So it's also true with the up quark and the down quark and the strange quark, etc. They could also.
Yeah, I sent some of my this thing in your research. I don't know whether you had my diagrams. I do.
Oh,
we'll
I haven't
talk
looked
about
at them
later.
yet. Can you?
I talk about later, but I don't know whether this. I talk about neutrino there for for possible formation. Maybe you can tie in with that. Anyway, maybe a part discussion in that. You know.
So anyway, so the Weinberg angle is around 13.5, but I would say it's probably. I just like coincidences, but I don't know if it's necessary.
Yeah, sometimes we don't know enough of these things. We have to find correlations and things like that, and that's how we can find out. Because I believe in serendipity. You know what I mean? Suddenly you come some connections, and that's how things work. Because I have found in my previous one, same thing. Serendipity played a very important role. That's how I figured out the connections, and then I work, because you can't get conjectures from that, and you work on it. A lot of times it works out. 50%. I find close to 50%. It's a guess. It's like a toss-up, but 50% in that sense is very high.
Yeah, true.
So you cannot totally dismiss that. You are, and there is a way I use something called matrix protocol. I will talk about later. It's a linguistic logical thing, logical connection. And from there, I can rule out. The first one I use, instead of true or false, I use true, not true, false, not false, true, not. So 4 things I use, not true. And that's important. And you say, if you say something, I'll say you can almost figure out it's false or not true. You can eliminate that easily. But 2 things you cannot eliminate, not false and true. Some things may be not false. That's where it belongs to. The kind of thing we are talking about, a lot of it belongs to not false. But it's not necessarily true, because we have to prove it. We have to prove it by derivation, by theory, and by experimental validation, verification, that all the reviewers are talking about. So I agree with that. But most of the things, like even I think general relativity and quantum mechanics fall in the category of not false. They're not really proven true, because you have vacuum catastrophe and other inconsistencies like CPT problem, the charge polarity time reversal problem, which has not been resolved. So it actually belongs to not false. But they're not false or not true. No, they are either, because there are many things that point to that, like gravitation waves, things like that. It partly proves the general relativity. But the falsibility aspect, that like the Popper things and other philosophy that talk about the falsibility criteria, it doesn't really satisfy that. So I am working with another person called Emery Taylor about discontinuum physics. And in our next paper, we are going to include that. He may come in as a 4th author, we'll see. And if Steve is interested, he can also join us in that publication. But essentially continuing with our circuitry and then doing the Hamiltonian and all those things, you know. And,
yeah, I noticed that Hamiltonian thing. I think I kind of misunderstood that initially. I thought it was like part of the calculation of the quantum computer, but apparently it's just the quantum computer is the many body system, and in order to simulate what's going on in the quantum computer, you need to use the Hamiltonian. So that would all be just, I think that would all just be like contained within the system.
Yeah, we don't worry about it. Like I said, we don't worry about this paper. I'm not going to touch upon that now because the reviewers will catch on it, right? We will do it in the next paper.
Oh, very good, very good.
After we publish.
Hey, Stephen, sorry.
Steve, so continue, Stephen. Sorry for interruption.
It's okay. It's okay. I'm just wondering, do you guys know about Quaternions?
Yeah, I'm big into
Christopher knows a lot. Christopher knows a lot about it.
I do quite like Quaternions, yes.
Well, I know nothing about them except that there's one guy in ResearchGate who keeps talking about them, but I ask him if he can give practical use to them by looking at my data, and he says no.
Okay.
I have yet to find anybody who can look at my data and throw it into Quaternion realm and work with it. So, you know, that's open.
Okay, cool. Yeah. It's always good to,
I also like to get into that. Christopher, I'm sure he's expert in that. So, but I also like to get into that if possible. Yeah.
Yeah, absolutely. I like, definitely like finding extra dimensions. So at the moment Stephen, you have, if I'm not mistaken, you have 3 dimensions, X, Y, and Z, refractive density, and probability.
Refractive index, density, probability, and you keep not saying the word temperature because I don't say it very much. That's because, let's see if I can get back here, somewhere here. I believe I do have. I've been trying since 1965 to bring temperature into this. If I could have percentage coming out of that plane, and then I could have refractive index, wavelength, and temperature.
Yeah. And then percentage being the E percent, is it, or something?
Well,
or no?
You remember I assign each fragment lesser, equal, or greater than the liquid refractive index.
Yeah.
So I speak in terms of lesser, L percent, and E equals percent. And in my 1972 dissertation, I came up with a P, thinking of E percent as being an uncertainty factor, because what happens is when you're looking at the fragment and you come to exactly matching where it's resonating with the liquid, it disappears.
Okay.
It disappears. So if you change, let's say, the temperature, so where am I here? Okay, it's backwards, so I have to think about what I'm doing. So here you can see the fragment, or you can see, which finger am I waving? You can see.
So good for me.
You have a zone of match, okay?
Yeah.
You can see the fragment. You can't see the fragment. You can see the fragment. You see what I'm saying?
Yeah.
They become transparent or something? They become optically transparent?
Let's assume the fragment is transparent, but if you're not in a zone of match, you can see it.
Oh.
Okay. That's interesting.
But if you do get to the zone of match, it disappears. So an equal count is kind of like an uncertainty factor. So I took half of E and added to L and got what I call a P percent, which I've modeled for a while, okay? That's all in my dissertation, which I can give you a copy of. But anyway, so more recently, you know, a few years ago at this point, I decided let's just work with L percent plus E percent, because that's the total signal.
Oh, all right. Why don't you have a greater than %?
Because if you know L and E, 100% minus total L and E equals greater.
Okay. So right. So you have these. Is temperature taking the place of probability, or are they the same thing?
No, temperature is involved in setup.
Right. So you have 4 axes then, including temperature.
Right here, I have refractive index, wavelength, and temperature. Coming out of this, according to this textbook, which is this reference.
Very good, very good. So you have 4. You have 4 axes here. Sorry.
Yeah, but it turns out from all my work, I was once asked when I was on stage, how well do you know the temperature? And I said, within a degree. Well, it turns out that my modeling tells me I know temperature essentially perfectly.
Right.
So I don't really need it in my plots.
Oh. Okay.
Because in order to control temperature, ever since my dissertation work included it, I have a thermistor which is calibrated. And if I know what the ohms on a step decade resistor box are, I can say what the temperature of the thermistor is.
Right.
All right. And I had
so because you have a perfect reading, that information drops out of your data set.
Right. I don't really need it in there.
Okay. And what about time? You said that was important.
Oh, only because drift of the experimental setup.
Oh.
For instance, a thermistor might age.
Oh. Okay.
Okay.
Yeah.
So that's why I have what I call D Julian as a variable.
Right.
How many days into the experiment I am.
Is it like a diode effect? The Mr. has a diode effect?
A thermistor is a thermistor. I'm not an expert on thermistors.
Okay. Because diode effect means the temperature can do inversions, can do opposite things.
I don't know.
Okay, that's fair enough. So let's say if temperature was, just hypothetically speaking, temperature was a dimension that was useful to you, you could like then plot a 4-dimensional graph using quaternions. So that's one use you could have for them. And that would really just be, well, I mean, in a way, you could just plot it without quaternions and just add the information in on a 4th-dimensional axis, like a 4-dimensional array or whatever, and then use those. What are the transformation matrices you need to rotate a 4-dimensional object? You could use the quaternion matrices to do that, you see. And yeah, so then you'd be able to, but really you'd just be moving through data that you know very well by the sense of it, but looking at it from a different perspective.
Yeah, I've decided it's really not all that important to me. But somebody trying to work with my data and trying to tie it into quantum theory might find something useful. I don't know.
Okay. Yeah. Well, I mean, I was just noticing there, if you could tell me for sure the specific angle you meant, like 13.5, that could have something to do with the Weinberg angle, which is pretty important.
I don't know what the Weinberg angle is. Maybe you can tell me.
Yeah, actually, Rajan, you were asking about that. Does that relate to the Higgs and its mechanism? And yeah, it absolutely does. It's I think during my presentation, I did a lot of stuff on the Weinberg angle.
Yeah, there are a lot of questions on that, but we'll come to it later. The second paper or subsequent paper will be addressing these things. Because right now we are trying to get this one focused on this one, but I think then we can apply this to start understanding the standard model and things like that. And your work will start automatically coming into the picture. Because you have done a lot on this one, Higgs boson, as well as the Weinberg angle. You know,
definitely.
This is my microscope.
Lovely.
It used to cost like that.
In our circuit, there is a spin. Each particle of the particle can spin. Okay. Then you have a rotation around that vector, magnetic vector, and also there'll be a revolution of the whole assembly. So these are the three. So we have to use spherical coordinates because there are three angles we have to talk about. Three-angle rotation, and there is functors and all. Because functor means different category, you know.
Right.
So, but we won't touch that.
To use like classes or something.
Yeah, in that diagrams, I have put those things, a brief thing. You know, we are not going to, because in this paper, I don't want to go into detail about that, but later on, we'll say, you know, it's beyond the scope, like you mentioned, and we'll stop at that and we'll move on. And the only thing I have not done much is you talk about some circuit building. I don't know how much you can do, but I'll see whether you can do that. But these things, these diagrams, you can see very useful, and you can create some graphs for that.
So you would like, so if I was to just summarize then, Rajan, for this paper, I'm going to make these, I'm going to like make these diagrams look a bit more formal maybe. And I'm going to give them back to you, and you are going to,
and you can put some graphs associated with that if you, whatever you find from there.
Sure.
So you can add to the analysis and put some graphs from it. That will, you know, that will be more authentic, you know.
Perfect.
It'll all tie together.
And then the last thing was you're going to tell them that maybe figures aren't necessary because the circuit's not been built yet. And finally, or there might be one or two things, you need to talk about limitations maybe?
Yes, limitations, exactly.
And
limitations, and then what we are talking about is, you know, something that we have to further simulate, program, which will take, like you said, it'll take a longer project, like months of project. And you can be mentioned about that. We are going to start that, but it'll take many months, and we plan to do it only in our subsequent papers.
Great. So, but there was one.
These five figures I have given, 5 diagrams with each one a lot of sketches and, you know, scenarios and all that. So you can look through that and see what you can, and you, like you mentioned, how to put it in the paper. You can put it, you know, and then redraw using your computer, things like that, because you are more IT expert. You can do that and then do the graphs or associated graphs, whatever you can do, some, you know, brief analysis of that. I don't know whether you can get the numbers, but some kind of a, you know, whatever you do.
How would I get numbers actually? Sorry.
Quantitative thing. Like from your rotation, you rotate pi by 2 or pi by 4, what will happen?
Yeah. Oh, right. So you want me to rotate this circuit maybe if I can by those degrees?
In the circuit, each one like a spin, like electron has a spin, each one has a spin. So you can put an angle of spin, like few angles of spin, and what happens to the circuit. And then when you rotate, like you have magnetic tensor and the other things are rotating, what will happen then, like pi by 2 or pi by 4, a few rotations. And the other one is the whole assembly is revolving, right? So what will happen? And I mentioned that one may be this, you know, may have attractive features. The other one has repulsive features. And what I have put the scenario. I briefly analyzed what will happen if it's attractive, what will happen if it is reflective. The space-time will either compress or it will, you know, or expand depending on that. And we may form neutrino or something like that. So these possibilities are there. And even phonon. And you can look at that, you know, whether it makes sense. And then if it makes sense, validate with some graph or a little bit of, you know, data with a few rotations, you know.
I don't think that's going to be, that's not going to happen for this paper, Rajan.
Yeah. I mean, you can just mention, you know, from what you know from there, whatever is possible, the graph, whatever is possible, whatever a possible thing we want to deduct from it, eventually.
I think you should mention that, Rajan. The faster you know this stuff that you're saying here, if you think it's important, make sure you put it in the paper.
Yeah, but whatever you can, whatever you can from your point of view, looking at it,
Right.
And
yeah.
you said you are going to put it. Yeah.
I'm still kind of learning here on the front of the circuit. Like I'm very interested, and it'd be interesting to see if I can model it, but without even, there's not much. There's only a limited amount I can say about
it. We won't touch too much detail, but whatever you can do, and so that you can put it into a computer, into a graph, so that we can present it. I don't think I can just put it my sketch into the paper,
No, I'm going to redo your sketch. I'll take a look at it and see what I can do with it.
And then you can simplify whatever you feel. It may be too complicated. We may not use all of it. The next paper we can use it, but whatever makes sense and simplify. Because it should not confuse the reviewers. That's what we have to be very careful that it ties along with what we have. We don't want to change the whole thing. The
last thing then, Rajan, or no, maybe it was second to last or maybe last. But so like if you had to come up with a limitation of your circuit right now, what would it be?
Yes.
Anything.
The limitation is that we don't know exactly the interactive features of the circuit oscillator. It's too complicated for us without further understanding and verifying the oscillator behavior.
I'm going to have to interrupt you there. That's a limitation on our end. That's not a limitation of the circuit. That's just like, we don't know.
Yeah, our end, we don't have the capability to, the circuit is that, we don't know the size of that circuit. The limitation is that, is it the Planck level or, we know it's like 10 to the power minus 2040. That's our estimation, which is a few orders of Planck length. But we don't know the actual size of the thing and how it, because we don't know also the time crystal. Time crystal is a new, concept from that Nobel laureate, Frank Wilczek.
Yeah, very, very interesting. Okay, so
those are limitations. We don't know that enough. So this seems to be plausible, but we need further validation, further. So those are the limitations.
Yeah, I thought the time crystal was a. Do you mention that in the paper?
Yeah, I think so. Briefly, we mentioned. I had to second look at it, but I think we briefly mentioned.
Okay, I don't remember seeing it, but if it was brief, then I mean, there's a lot.
Either this paper or something that referred to another paper. We are referring to another paper. It is there in another paper, I think. I look at it again. Okay, but if it's not there, we don't have to worry too much about that.
Yeah, it sounds like it's a massive concept. Like, it nearly contains.
You know how he came up with the Nobel laureate Frank Wilczek? He was giving a lecture, and during the lecture, he came up with this concept.
Wow. Yeah. That's a cool concept, and they're working on it now, aren't they?
Yeah. Google. I think that's I think explains our circuit also very well. I think that's a good start, a good this thing. Later on, we'll pick up on that.
Chris had one more thing to ask.
Okay. Sorry again, Steve. Please go ahead. We are keep interrupting you.
Chris, that's okay. Chris had one other thing to ask.
Oh, yeah, there was a couple of things. Yeah. Well, just from my notes, because I've lost the thread of my thought from earlier. Well, I did notice Joe Hoagland in your emails. He's not related to Richard C. Hoagland, is he? Stephen?
You're talking to me?
Yeah, yeah.
I don't know. I don't know.
Oh,
I can't remember the name of the guy I tied to immediately when I was looking for 19 point whatever.
Okay, right, yeah. And then there was Divine Cosmos. Who's the guy who runs that? Is it
Brian somebody, right?
Yeah, I have, I've touched bases with all these people, but I don't have them all sorted.
That's fine. So this microscope costs $269 back.
Yeah. That's like in the 1960s.
So that was, so what's that in today's money? Like
I don't know. The point is you can't get these anymore, and I have one. And
right.
I just want to talk about it.
I have used similar one called size microscope. I have used.
Okay, so the point I'm trying to make is this is a student microscope. My work is supposed to be simple. It's supposed to be done by anybody with any microscope. Okay, but I want to show you what I've done with this microscope. I've got resistors underneath to heat the stage.
Okay, interesting.
I have, here's a thermistor pair inside of a glass slide.
A lot of sensors,
which is
a lot of resistors.
You keep talking. Which is taped into place so it doesn't move. Okay. I have a washer underneath to collect heat and redistribute it as it comes up and through. And I have, you can see the setup.
Yeah.
And I have resistors also around the objective lens, which is a 40 power. I get 400 power with a 10 power ocular, and this comes right down on top of the slide. It's very, very close in order to see.
Is that that's doing some heating as well?
Yes.
And so close to the lens? Does that not have
Yes.
That's crazy.
I dared. I took I took dichroic filters and I put them on a very hot light, white light lamp with a diaphragm to clamp them into place. And I shone that down. And I also sometimes had an infrared lamp shining at the whole region, all of which were clicking on and off according to the thermistor and the settings on my step decade resistor box. So that effectively the temperature was perfectly controlled.
Wow.
This is after having pictures of a hood that I built on my desktop, trying to keep everything stable. This is after having shoot, where am I? Oh, this is the wrong. Where is my refractometer? Oh, here we go. This is after having built my own instrument, which in order to show you, I have to open with. Okay.
Oh, you built your own?
Yes, this is my own refractometer.
Wow.
This is a modified, this is a jelly refractometer, okay? One is supposed to put one's eye here, and light is coming through a slit behind this, and one looks here, it's covered up. This is covered.
Yeah.
There's a heat source under there. That's a soldering iron, okay? Yeah. And one is supposed to look with his eye right there and slide this thing up and down according to where the line of refraction is seen to be on the scale. And instead, at my office, one room length away from the sodium light through this jelly refractometer, I had a scale set up on a bookcase. And I would run across by the desk of the poor gal who was sharing the office and climb up there and take 10 readings with a very sharp, you know, that long a pencil point and do that 10 times and then score where the lines were on the scale and go over and enter onto the computer and get an average reading and then change something and do it again and do it again and do it again. Instead, I ended up building my own instrument.
Cool.
Because Klaus Kyle said, but Steve, what if you had an earthquake? Which would have changed the dimensions of the room. So I made one that would be less likely to be changed by an earthquake. And it's over there in the corner.
Nice.
In that box that's not, in that box way over there. Cool. In the corner somewhere. I can't now my thing is all wapple wally.
So tell Stephen, I've got another paper here, vacuum structure energy joules mapped over the Emmons surface. Is that a paper?
Which paper are you looking at?
Oh, it's not on your screen, but it's on ResearchGate, and it's called Vacuum Structure Energy joules. Is it your paper? It's in chat. I posted it in chat.
Oh, hold on. Let me see if, where am I here?
And I'll also get.
Let me see if, what in the world am I looking at?
It's definitely your paper.
Yeah, hold on. I think it's B. Okay, give me some control here over what I'm doing. What is this? Lord. If this thing would go away. There. Okay, so it's one of these. It might be this one. I don't know. Maybe it's this one.
Yeah. Not sure.
No. Is that it?
No, if you go down to chat at the bottom of this, at the bottom of the screen, beside participants.
Wait, for me, chat is at the top of the screen.
Okay. And then just click on chat, and then there's a message from me to, yeah, that's the one.
Yeah, and your name is there.
Yeah, it's definitely.
Yeah,
How old is that? Not that old. Less than a year.
Yeah, this year, let's see here, down here.
There's the C mount. Cool.
Oh wait. This year, I have published these 4 papers and had this one rejected. Okay.
Very good.
So,
okay.
The vacuum structure, I think what you're referring to is this paper.
Okay.
Okay. Essentially.
Yes.
Okay,
right.
That was leading up to this. What I'm sharing is my work notes in what you just landed on. Okay.
Yeah.
Yeah. So you probably read work notes, but here's the paper in which this is my what I call 2021B in my current references.
Yeah, okay. I've read that paper.
Yeah. So this is where I came up with the ability to model the density function that I showed you, where I divided the refractivity by density in order to get the K value.
Yeah. And what is the density? Is that the density of the material?
Yes.
Right. Okay.
Yes. But what I have discovered is there are very few references to literature where K values have been published for various minerals. I can't find very many. And anyway,
so there might be another dimension. Would it to your data set, the K value, and then the KP and KC, would they all be different?
Yeah, I believe that I have showed you the only ever, where am I? I don't know where I am anymore. How do I get this thing to move? There. I believe this is the first ever K values published or tried to be published for any total rock specimen ever.
Cool. And so what do you think this is, what do you think the military could be doing with that? Remember you said?
They could have drones and fly by and use refractive index to cloak things or whatever they do. I don't know.
Oh,
Can you get topography from it? Can you follow a topography?
In Golden software, I can do all kinds of things.
Like if they go to a place and they want to identify a place, right? Drone, suppose they're dry, can they use this data to find out exactly where they are?
I see what you're saying. You're not talking about my data in particular. This is topography of K values. It's a topology. It's not really topography. Okay. But if you're saying, what can they do as they're flying a drone over a mountain? Maybe they can tell what the refractivities are of the mountain rocks. You know, maybe they can do all kinds of things I can't even think of.
Yeah.
Whatever they do, and why they would classify refractive index work, I can't answer.
Okay.